Bluetooth. Get it straight.
Okay, let's take a look at the sonar transducer problem that we were dragging from a boat in the class. This is a similtude or modeling problem where we're going to use wind tunnel or other results as our model to scale up to the real case, which is the prototype. So we've got the prototype, which is the boat dragging the sonar through the ocean, and we've got the model, which is a similar object that's put in a wind tunnel to determine how much drag will happen on that. So a couple of things that are different here. One, the sonar object is actually 1 foot in diameter. The model system is only 6 inches. And obviously the wind tunnel is working with air, and the sonar is being dragged through water, and it's pretty cold water, so we'll have to track the viscosity on that. So the key here is if we assume that the problem, the model is similar to the prototype system, then the dimensionless groups are the same. So we have this drag coefficient, which is actually the force of drag divided by this energy term rho v squared d, so that's the velocity squared times the diameter. And that's going to be a function of the Reynolds number. So there's basically 2 pi groups here, the one related to the drag coefficient and one related to the Reynolds number. So for similarity, the model Reynolds number has to be the same as the prototype Reynolds number, and the model drag coefficient has to be the same as the prototype drag coefficient. So we know enough from the given information about the prototype to calculate a Reynolds number, because we just need the velocity, the diameter, which we have, and density and viscosity terms. Remembering that we can also use this new term, new NU, not NEW term, to be the kinematic viscosity, which is just mu, regular viscosity over here, divided by the regular viscosity divided by the density. So if we look that up for seawater someplace at 5 degrees C, we would get this number. So that's a lookup number. The velocity is 5 nautical miles per hour. That's what a knot is. So that's kind of strange. So we had to convert that to 8.44 feet per second. And if we did all that, we would get a Reynolds number of about 500,000. So we are given, remember back up here, that the force of drag on the model in the wind tunnel is 5.58. And so that would tell us what speed the wind tunnel is run at. And knowing that we have the same Reynolds number for the wind tunnel, that's what we just assumed when we said that we have a similar system. So that's how this modeling works, and that's really the key to these problems, is you calculate the Reynolds number for one side, but then what for the other side. So we can say that the Reynolds number is known. We can calculate what the wind tunnel velocity would be. Remember, now we're going to put in the viscosity for air, which is another lookup number, and diameter, which we're given, has 0.5 feet now. We're in the model system. So if we do that, we see that the model is running much faster with air, and you need more speed in order to generate the kind of drag that you would expect when you're dragging this thing through water. So then you can go back to your drag coefficient expressions here. And those also have to be equal. And we know everything except the force we expect on the prototype in the ocean. So we're given this one, remember. That comes from the wind tunnel. And all these guys are lookup terms. These guys are ones we calculated or given, and the diameters were given. We just put those all together, and we see that this is the kind of force we should expect on the prototype sonar system in the ocean.